All right, so we're going to do a higher level equation today, just so that we can see what this would be used for in real life. So in real life, you could be given these givens, 12.5 grams, which we know is a mass, so that's part of our decoding. Sometimes the equation doesn't tell us, but we know grams is mass. Negative 222.5 J, that is equal to our Q value. Okay, and 25 degrees C, that's our temperature final. That's where we ended at. Temperature initial is our start temperature. Okay, and now when I look at this and I go for my U, what am I missing? What's that equation? Q equals MC delta T. I have a Q, I have an M, and I have two temperatures, so I have a delta T, but I don't have my C value. And that's where it comes into important. If we're finding a material something and I know the C value, I can match it up on this chart. And the other equation we're going to need, or the other thing we're going to need to find is percent error. So we actually have three equations this time. Q equals MC delta T equals temperature final minus temperature initial, and we have our percent error one, which I do not want to, well, I guess I can put it over here. Percent error is equal to, in this case, the table value, because it's the book value, minus my experimental value over the table value times 100%. So I got three equations going on here. What do I need to start with? My delta T. Delta T is equal to final, temperature final. So it's 25 minus 50 degrees C. So my delta T is actually going to be negative 25 degrees C. That's weird. That's a negative temperature. It's not so weird. It just means it's exothermic, because that temperature started out high and it went down, which means the heat exited. Exit, thermal heat. Okay, so we know it's exothermic. And so that's just another clue that we have in our package. Okay, our Q, when we substitute that in, negative 222.5 joules is equal to 12.5 times C times negative 25. And now I need my little calculator. I'm going to divide the right side by negative 25. What I do to one side, I do to the other. Those terms on the right side cancel out because they weren't subtracting there. They were being divided by. So I need negative 222.5 divided by negative 25. Notice I didn't use the minus sign for any of that. And I got 8.9. So now it's 8.9 equals 12.5 C. Again, divide by 12.5 because it's attached to the C and I want to get C by itself. And what I do to one side, I do to the other. 8.9 divided by 12.5 is 0.712. I look back at my sig figs, and okay, I have 3 sig figs here, 1 sig fig there, 4 sig figs there. So C equals 0.7. Okay, and now what do I think it is? I look at my chart. Oh, I think it's sulfur. Now, they asked me to figure out how close am I to thinking it's sulfur. That's when I use my C value and compare it to my other C value. My table value of sulfur is 0.71. My experimental value, because it's not as precise, is 0.7 divided by 0.71, the table value, times 100. Plug that into my calculator. 0.71 minus 0.7 equals, make sure you hit that equals to pause here, or use parentheses around the 0.71 minus 0.7, divided by 0.71 times 100. 1.408%. 1.408%. And now I need to go back and still look at sig figs. So there's only one sig fig here. So if it didn't say keep answer in one decimal place, then you would round to one sig fig and get 1%. Now, oftentimes they will tell you keep one decimal place just so you can see it. But in this case, it didn't. So we're going to use our sig fig rules. So where our experiment was 1% off, that's actually pretty awesome. That never happens. Well, I shouldn't say it never happens, but if we were in class and not virtual and doing this experiment, we probably wouldn't get numbers like this.